Louis Victor Pierre Raymond de Broglie was born on August 15, 1892, into one of the most distinguished aristocratic families in France. The de Broglies were not merely nobility, they were a dynasty that had shaped French and Italian history for centuries. His family held the title of dukes, possessed vast estates, and moved in the highest circles of European society. Louis was born at the family mansion in Dieppe, a seaside town in Normandy, into a world of privilege, elegance, and tradition. He was the youngest of 5 children, and from birth, his path seemed predetermined. He would be educated in the classics, groomed for diplomacy or public service, expected to uphold the family's prestigious name. Science was not the obvious choice for a French aristocrat. That was a domain for the middle classes, for those who needed to make their way through merit rather than birthright. But the de Broglie family had an unusual tradition. Louis's older brother, Maurice de Broglie, had already broken with aristocratic convention by becoming a physicist. Maurice was 17 years older than Louis, almost a father figure, and he established one of the finest private physics laboratories in France in the family's Paris mansion. This wasn't just a hobby. Maurice was a serious experimental physicist, working on X-rays and spectroscopy, publishing significant papers, hosting meetings with leading scientists. The young Louis grew up in a home where dukes discussed diffraction patterns over dinner, where Nobel laureates were family friends, where the boundaries between aristocratic society and scientific inquiry had already been breached. Initially, Louis followed the expected path. He studied history at the Sorbonne, earning his degree in 1910. He seemed destined for a career in the diplomatic service or perhaps as a historian, but he couldn't escape the pull of science. He attended his brother Maurice's scientific gatherings, reading the papers being discussed, listening to the debates. The first Solvay conference took place in 1911, bringing together the greatest physicists in the world to discuss the emerging quantum theory, and Maurice was there. Through his brother, Louis had access to the cutting edge of physics even before formally entering the field. By 1913, after completing his history degree, Louis made his decision. He would study physics. His family was surprised but not disapproving. Maurice had paved the way, and the de Broglies, despite their aristocratic heritage, valued intellectual achievement. Then came World War I, and Louis de Broglie's scientific education was interrupted by service. He was assigned to the wireless telegraphy section of the army, stationed at the Eiffel Tower, which was being used as a military radio transmitter. It was an unusual position for an aristocrat, but Louis took it seriously. For 4 years, he worked on radio communications, learning about electromagnetic waves, about transmission and reception, about the practical side of wave physics. This experience wasn't wasted. Years later, when he developed his theory of matter waves, his intuitive understanding of wave phenomena, gained during those war years at the Eiffel Tower, would prove invaluable. War is often seen as an interruption to scientific careers, but for de Broglie, it was part of his education, a practical apprenticeship in the physics of waves. When the war ended in 1918, Louis de Broglie, now 26 years old, returned to physics with renewed determination. He began working in his brother Maurice's laboratory, helping with experimental work on X-rays. But Louis's mind was drawn to theory, to the conceptual puzzles that were tearing physics apart. The quantum revolution was in full swing, and physics was in crisis. Since 1900, when Max Planck introduced the quantum of energy to explain blackbody radiation, physicists had been forced to accept increasingly bizarre ideas. Light, long understood as a wave, sometimes behaved like a particle. Einstein had shown this in 1905 with his explanation of the photoelectric effect. Atoms could only exist in certain discrete energy states, not the continuous range classical physics allowed. Bohr's model of the atom worked, but no one understood why electrons could only occupy certain orbits and not others. The situation was deeply unsatisfying to many physicists. There were 2 sets of rules, one for the macroscopic world of everyday objects, where classical Newtonian mechanics worked perfectly, and another for the atomic world, where quantum rules applied. But where was the boundary? Why should nature have 2 different sets of laws? And most puzzling of all, light exhibited wave-particle duality, behaving sometimes as a wave and sometimes as a stream of particles called photons. This was accepted, however, reluctantly, because the experimental evidence was overwhelming. But it seemed arbitrary, exceptional, a peculiarity of light. Matter, electrons, protons, atoms, these were obviously particles. They had mass, they could be localized, they collided like billiard balls. No one seriously thought matter could be wave-like. No one except Louis de Broglie. In the early 1920s, working in relative isolation, he was never part of the major research centers like or Copenhagen where most of quantum mechanics was being developed. De Broglie began to think about symmetry. If light, classically understood as a wave, could sometimes behave as a particle, why couldn't matter, classically understood as particles, sometimes behave as waves? It was a simple question, perhaps even obvious in retrospect, but no one had asked it. Or if they had, they dismissed it as absurd. Electrons were particles, everyone knew this. You could see their tracks in cloud chambers, measure their charge, count them individually. How could something so obviously particle-like be a wave? But de Broglie took the idea seriously. He began working out the mathematics, trying to develop a consistent theory. If electrons were waves, what determined their wavelength? Working from Einstein's and Planck's quantum relations for light, de Broglie proposed a stunning hypothesis. Every particle has an associated wavelength, given by lambda equals h/p, where lambda is the wavelength, h is Planck's constant, and p is the particle's momentum. High momentum particles have short wavelengths. Low momentum particles have long wavelengths. For everyday objects, baseballs, cars, people, the wavelength is so incredibly tiny as to be unmeasurable and irrelevant. But for electrons and other atomic-scale particles, the wavelength is comparable to atomic dimensions, and wave effects should be observable. It was an audacious proposal, and de Broglie knew it. He was proposing to overturn centuries of understanding about the nature of matter. But the mathematics worked out beautifully. When he applied his wave hypothesis to the Bohr atom, suddenly, the mysterious quantization of electron orbits made sense. Electrons could only occupy orbits where their wave formed a standing wave, where an integer number of wavelengths fit exactly around the orbit. It was like the harmonics on a guitar string, only certain wavelengths are allowed. The arbitrary-seeming quantum rules of the Bohr atom weren't arbitrary at all. They were consequences of the wave nature of electrons. De Broglie had found a deeper explanation, a unifying principle. By 1924, he had compiled his ideas into his doctoral thesis, perhaps the most revolutionary PhD dissertation in the history of physics. In 1924, Louis de Broglie submitted his doctoral thesis to the Faculty of Sciences at the University of Paris. The thesis, titled Research on Quantum Theory, was only about 70 pages long, but those pages contained one of the most important ideas in 20th century physics, the wave nature of matter. His thesis committee must have been bewildered. Here was an aristocrat, a relative latecomer to physics, proposing that electrons, solid, concrete particles, were actually waves, or at least had wave-like properties. It was the kind of wild speculation that would normally be rejected out of hand. But de Broglie presented his case carefully, showing how his hypothesis explained puzzling features of atomic physics, how it provided a natural explanation for quantum phenomena. The committee didn't know what to make of it. One of the examiners, Jean Perrin, thought the work was either brilliant or crazy, possibly both. Unsure how to proceed, the committee did something unusual. They sent a copy of the thesis to Albert Einstein, asking for his opinion. Einstein was, by 1924, the most famous scientist in the world, the man who had revolutionized physics with relativity, who had pioneered quantum theory with his work on the photoelectric effect and specific heats. If anyone could evaluate de Broglie's radical proposal, it was Einstein. Einstein read the thesis carefully, and his response was unequivocal. De Broglie's work was not only correct, but represented a fundamental advance. He has lifted a corner of the great veil, Einstein wrote. With Einstein's endorsement, the committee awarded de Broglie his doctorate. But a doctoral thesis, even one endorsed by Einstein, doesn't change physics unless it's verified experimentally. De Broglie's wave hypothesis made a clear prediction. If electrons are waves, they should exhibit wave phenomena like interference and diffraction. When waves encounter obstacles or slits comparable to their wavelength, they create characteristic interference patterns, bright and dark bands resulting from waves reinforcing and canceling each other. This had been demonstrated for light in the famous double-slit experiment. If electrons were waves, they should do the same thing, but no one had ever seen electron interference. Electrons seem to travel in straight lines like particles, not spread out like waves. Then, in 1927, 3 years after de Broglie's thesis, two American physicists, Clinton Davison and Lester Germer, made a discovery. They were studying how electrons scattered off nickel crystals, routine materials science research, nothing to do with testing quantum theories. But they noticed something odd. The scattered electrons showed a pattern that looked remarkably like the diffraction patterns produced by X-rays scattering off crystals. When they analyzed the pattern quantitatively, they found that the electrons were behaving exactly as de Broglie had predicted, as waves with wavelength lambda equals h/p. Almost simultaneously, George Paget Thomson in England demonstrated electron diffraction by passing electron beams through thin metal films, again confirming de Broglie's formula. The experimental vindication was complete and rapid. Within 3 years of his thesis, de Broglie's wave hypothesis had gone from speculative theory to established fact. The impact was immediate and profound. Erwin Schrödinger, working on his wave equation in 1926, was directly inspired by de Broglie's work. Schrödinger's equation is essentially a wave equation for matter waves. Werner Heisenberg's uncertainty principle, formulated in 1927, makes sense in the context of wave-particle duality. Waves, unlike particles, don't have precise positions and momenta simultaneously. The entire edifice of quantum mechanics rested, in part, on de Broglie's insight. In 1929, just 5 years after his thesis, and only 37 years old, Louis de Broglie was awarded the Nobel Prize in Physics for his discovery of the wave nature of electrons. It was one of the fastest paths from PhD to Nobel Prize in history, a testament to the fundamental importance of his contribution. But de Broglie's relationship with quantum mechanics was more complicated than this triumph suggests. While his matter-wave hypothesis was universally accepted and became a cornerstone of quantum theory, de Broglie himself was never entirely comfortable with the standard interpretation of quantum mechanics that emerged in the late 1920s, the Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg. According to this interpretation, quantum systems don't have definite properties until they are measured. The wave function describes not an actual physical wave, but a wave of probability. An electron doesn't have a definite position before you measure it. It exists in a superposition of all possible positions, and measurement somehow collapses the wave function to a single outcome. This probabilistic, observer-dependent view of reality troubled de Broglie, just as it troubled Einstein and Schrödinger. In his original thesis, de Broglie had imagined matter waves as something more concrete, actual physical waves somehow guiding the motion of particles. He developed this idea further into what he called pilot wave theory, or double solution theory. In this picture, particles are real, localized objects, but they are accompanied by a physical wave that guides their motion. The wave tells the particle where to go, like a pilot guiding a ship. When you have many particles all guided by the same wave field, statistical quantum behavior emerges, but individual particles always have definite positions and follow definite trajectories. De Broglie presented his pilot wave theory at the 1927 Solvay Conference, the famous meeting where the founders of quantum mechanics gathered to debate the interpretation of the theory they'd created. But his presentation didn't go well. Wolfgang Pauli raised objections, questioning whether pilot wave theory could handle certain quantum phenomena. De Broglie, never a forceful debater and somewhat intimidated by the aggressive questioning of Pauli and others, couldn't adequately defend his theory on the spot. The pilot wave interpretation was largely abandoned, and the Copenhagen interpretation became the standard view taught to physics students. De Broglie himself seemed to accept this, moving away from his pilot wave ideas and working within the standard quantum mechanical framework for the next several decades. But the story doesn't end there. In 1952, a young American physicist named David Bohm, unaware of de Broglie's earlier pilot wave work, independently developed a very similar theory, now called Bohmian mechanics or the de Broglie-Bohm interpretation. Bohm showed that pilot wave theory could handle all the phenomena of quantum mechanics, including those that had stumped de Broglie in 1927. When de Broglie learned of Bohm's work, he was reinvigorated. Here was vindication that his earlier instincts had been right, that there was an alternative to the Copenhagen interpretation. In his 70s, de Broglie returned to working on pilot wave theory, developing it further, writing papers and books arguing for its viability. The physics community remained largely unpersuaded. By the 1950s, the Copenhagen interpretation was entrenched, and most physicists saw no need for alternatives. Pilot wave theory was viewed as unnecessarily complicated, adding hidden variables, the definite particle positions, without changing any experimental predictions. If two theories make identical predictions, why choose the more complicated one? De Broglie argued that his theory provided a clearer picture of reality, avoided the measurement problem, and eliminated the observer-dependent weirdness of Copenhagen. But he was fighting an uphill battle. Unlike his matter-wave hypothesis, which had been rapidly confirmed and accepted, his pilot wave interpretation remained a minority view, respected but not embraced. Even today, though interest in alternative interpretations of quantum mechanics has grown, the de Broglie-Bohm interpretation remains outside the mainstream, though it's taken more seriously than it was in de Broglie's lifetime. After his Nobel Prize in 1929, Louis de Broglie's career entered a different phase. He was still young, only 37, but he had already made his great contribution. He continued to work on quantum theory, on relativity, on the foundations of physics, but he never again achieved the kind of breakthrough that had made his name. This isn't a criticism. Most physicists never have one revolutionary insight, let alone two. And de Broglie's matter-wave hypothesis was more than enough for a lifetime. But it meant that his later career was somewhat anticlimactic, at least in terms of revolutionary discoveries. He became a teacher, a mentor, an administrator. In 1932, he was appointed professor of theoretical physics at the Henri Poincaré Institute in Paris, a position he held until his retirement. He trained generations of French physicists, taught courses on quantum mechanics and wave mechanics, wrote textbooks that became standard references. He was a clear lecturer, patient with students, generous with his time. But he was also somewhat formal, reserved, aristocratic in bearing. His students respected him, even revered him, but found him distant. He never married, lived alone in the family mansion in Paris, maintained the dignity and reserve expected of his social class. There were rumors of a romance in his youth that ended badly, but de Broglie never discussed his personal life. He was intensely private, devoted to physics, but not given to the kind of personal revelations that would help biographers understand the man behind the theories. During World War II, de Broglie remained in Paris through the German occupation. It was a difficult time. Many scientists fled. Those who remained faced constant pressure to collaborate or at least accommodate the occupiers. De Broglie kept his head down, continued teaching as best he could, avoided politics. After the war, he was sometimes criticized for not having been more active in resistance, but it's unclear what more he could have done. He was not a man of action, not a political figure. He was a theoretical physicist, most comfortable in the realm of ideas, and he survived the war by being unobtrusive, maintaining his work as much as possible under impossible conditions. In the post-war years, de Broglie received numerous honors. He was appointed perpetual secretary of the French Academy of Sciences, a powerful administrative position. He received honorary degrees from universities around the world, gave lectures, attended conferences. He was France's elder statesman of physics, a living connection to the heroic age of quantum mechanics. In 1952, when he returned to work on pilot wave theory after learning of Bohm's work, some colleagues saw it as a kind of nostalgic return to his youth, a refusal to accept that his early ideas had been superseded. But de Broglie saw it differently. He believed he'd been right in 1927 that the Copenhagen interpretation was philosophically problematic, and he spent his later years trying to develop a more satisfying alternative. He wrote prolifically in these later years, not just technical papers, but philosophical reflections on the nature of science, on the relationship between mathematics and physics, on the conceptual foundations of quantum mechanics. He was concerned that physics was becoming too mathematical, losing touch with physical intuition, that young physicists were learning to calculate without understanding. These were the concerns of an older generation watching their field evolve in directions they found uncomfortable, but they weren't without merit. De Broglie represented a style of physics, intuitive, based on physical pictures and analogies, that was increasingly out of fashion in the post-war era of formal field theories and abstract mathematical structures. Louis de Broglie died on March 19, 1987, at the age of 94, in his family home in Paris. He had lived through nearly a century of extraordinary change, from the horse-drawn carriages of his childhood to the space age, from classical physics to quantum mechanics and beyond. He had seen his revolutionary idea vindicated, had won the Nobel Prize, had become one of the most honored scientists of the 20th century. But he died still somewhat frustrated, still believing that quantum mechanics, despite its empirical success, was philosophically incomplete, that the Copenhagen interpretation was not the final word, that his pilot wave theory offered a better way forward. His legacy is complex and multifaceted. On one level, it's simple and undeniable. The de Broglie wavelength, lambda equals h/p, is one of the fundamental relations of quantum mechanics. Every physics student learns it. Every quantum mechanical calculation implicitly uses it. Wave-particle duality, the idea that matter has both particle and wave aspects, is now so deeply embedded in our understanding of nature that it seems obvious, even though it was revolutionary when de Broglie proposed it. The entire framework of quantum mechanics, Schrödinger's wave equation, Heisenberg's uncertainty principle, the probabilistic interpretation of the wave function, rests on de Broglie's insight. Without his matter waves, quantum mechanics as we know it wouldn't exist. The practical applications are enormous. Electron microscopy, which uses the wave nature of electrons to image structures far smaller than visible light can resolve, is based directly on de Broglie's ideas. Modern materials science, nanotechnology, semiconductor physics all depend on understanding the wave nature of electrons. Quantum computing, which exploits quantum superposition and entanglement, relies on the wave-like behavior of particles. When we talk about quantum tunneling, quantum dots, or any phenomenon where particles behave in ways that classical mechanics can't explain, we're seeing de Broglie's matter waves in action. But de Broglie's legacy extends beyond this technical achievement. He represented a particular approach to physics, intuitive, based on symmetry and analogy, guided by a sense that nature should be unified and comprehensible. His great insight came not from experimental data. The data that would confirm his theory didn't exist when he proposed it, but from theoretical reasoning, from asking, why should light be special? And following the logic where it led. This kind of theoretical boldness, the willingness to propose ideas that seem absurd on their face but might reveal deep truths, is rare and valuable. Physics needs both the careful experimentalists who measure nature precisely and the bold theorists who imagine possibilities no one else has considered. De Broglie was the latter. His later work on pilot wave theory, though less celebrated, also left a mark. The de Broglie-Bohm interpretation remains a minority view, but it's a respectable one, taken seriously by philosophers of physics and by physicists interested in foundational questions. It demonstrates that the Copenhagen interpretation, despite its dominance, is not the only consistent interpretation of quantum mechanics. In recent decades, as interest in quantum foundations has grown and as experimental tests of different interpretations have become possible, de Broglie's pilot wave theory has gained renewed attention. It turns out that he was ahead of his time, not just in 1924, but also in 1927 and again in the 1950s. His interpretation was dismissed prematurely, and the questions he raised about the nature of quantum reality remain open. There's something fitting about de Broglie's story, an aristocrat who became a revolutionary, a man of privilege who overturned established truths, a theorist who imagined matter waves before anyone had seen them, and then lived to see his vision confirmed beyond doubt. He bridged worlds, aristocracy and science, classical physics and quantum mechanics, French scientific tradition, and the new international physics community of the 20th century. He was both part of the old world, the formal, reserved, aristocratic de Broglie, and the new, the quantum revolutionary who changed how we understand matter itself. His matter waves, once an absurd hypothesis, are now so fundamental to physics that we can barely imagine the science without them. Every electron, every atom, every quantum particle carries its de Broglie wavelength with it, a reminder of the insight of a French prince who dared to imagine that matter, like light, might dance to a wave equation. The waves are there, subtle and pervasive, underlying the solidity of matter. Connecting the particle nature, we perceive with the wave nature that quantum mechanics revealed. Louis de Broglie saw them first, not with his eyes but with his mind, and in seeing them, he gave us a new way to understand the quantum world that shapes everything around us.